Thanks for coming, everybody. We have Professor Allison Wing from Florida State University with us today. She's going to talk about acceleration of tropical cyclone development. Allison and I have known each other for a number of years, mostly because our research interests have overlapped quite a lot. Allison's research has covered convective aggregation, and she's kind of covered a range of things from very idealized radiative convective equilibrium simulations of convective aggregation to then also looking at things like tropical cyclones and tropical convection and how the radiative feedbacks influence the climate as a connection between the cloud structures and climate feedback. So the research has been, it's been interesting to see what she's done over the last number of years. I think she's clarified a lot of good questions. She did her PhD at MIT with Carrie Emanuel. She's originally from New York, not from Long Island though. That's all right. And then she had, let's see, postdoctoral research fellowship at Lamont Doherty through Columbia University. And then is it since 2017 you've been at Florida State University? So take it away. We also will have lunch in the Swanson room afterwards. So please join us.
Great. Well, thank you very much. Thank you very much, Levi, for the invitation. I'm happy to be here to talk to you guys today about some of the work I've done and my group has done on the acceleration of tropical cyclone development by cloud-radiative feedbacks. And I don't think that the importance of understanding tropical cyclone development needs too much introduction, but I do always like an excuse to show some satellite images of hurricanes. So this is the most recent strong hurricane to affect the United States this past fall, Hurricane Ian, which made landfall in Florida as a Category 4 storm with 150-mile-an-hour winds, underwent multiple episodes of rapid intensification as it approached land, which is one of the things that makes forecasting very difficult. And unfortunately caused significant damage and flooding, both immediately on the coastline near Fort Myers, Florida, as well as inland flooding from rainfall. And so I'm at Florida State University, which is in Tallahassee up here. We had a whole week off from classes for Hurricane Ian, and our only impact locally from the storm was absolutely stunning sunsets from the transverse banding and the outflow. So we missed it, but had the week off anyway. So when it comes to hurricanes or tropical cyclones, we're lucky in that our ability to forecast them has improved significantly in recent years. In particular, global forecast models are now a reliable source of tropical cyclone or TC genesis or formation guidance. And then on the climate model side of things, our models have also improved such that they can reproduce the tropical cyclone climatology with some fidelity and exhibit some skill in seasonal forecasting. And so this is just an example of one, on the left, one particular climate model and its hurricane tracks over a historical simulation compared to the observed hurricane tracks on the right. And you can see that this model does a pretty good job. You know, it generally puts hurricanes in the right places. And this is important because we don't currently have a physical theory for what sets the global frequency of tropical cyclones. And that means that our projections of future tropical cyclone activity rely heavily on global climate models. And so we need to have them be as skillful as possible. Now here I chose a good example, but if we look at a broader selection of climate models, we can see that they don't all do quite that well. And so even though the models have improved, substantial biases have remained. These are all sort of CMIP class climate models, and some of them, you know, basically don't form any tropical cyclones at all, or maybe they do some in some basins, but, you know, miss the Atlantic, like in this model here. And that's just on sort of the frequency and track distribution side of things. When it comes to intensity, things are even harder. Even high resolution climate models running at around 25-kilometer resolution still struggle to produce the observed distribution of TC intensity. So here, the TC intensity observed is in the black line, and all these different high resolution models are in the colored lines, and really none of them get storms of major hurricane strength or further. Now, resolution is a big part of this. If you go to even higher resolution, things do improve, but even across models at the same resolution, models can differ substantially. And so on the right here, this shows a particular bulk metric of the sort of global tropical cyclone activity, ACE. And you can see that at a given resolution, for example, half degree here, we can have a wide spread across models in their representation of the TC activity. And this is not explained by biases in a large scale environment. So it's not that, this model has, stronger wind shear than this one or something like that. That's on the climate model side of things. What about the forecast side of things? How has our intensity forecasting improved or not improved? Well, for a long time, there really weren't very much improvements in TC intensity forecast. So this shows the National Hurricane Center's intensity error at different lead times for different decades. And you can see for a while, these lines were really stubbornly not moving at all, even as track forecast improved. Finally, in the last 10 years or so now, we actually saw some intensity errors. So things have definitely gotten better, but challenges, especially regarding forecasting rapid intensification, which is when a storm increases by a certain amount in the 24-hour time period, still remain. And so the plot on the right here shows the probability of different forecasts from the NHC as well as different models detecting these instances of hurricanes intensifying by at least 20 knots in 24 hours. And while the probability of the forecast detecting that has increased, we're still only around 20% of the time, which is not very good. And so there's a variety of different strategies that are used to try to improve model representation of TCs and their forecasting. But I would like to argue that one of the things that needs to be part of that picture is a better fundamental understanding of the physical processes associated with tropical cyclone formation and intensification. There are many such processes out there, but the one I'm going to focus on talking about today is cloud-radiative feedbacks. And the idea with these cloud-radiative feedbacks is that deep convective clouds typically have cooling at their cloud tops and localized warming below the cloud base. And so these deep clouds that have lots of water vapor and ice crystals create this localized greenhouse effect that can trap heat and warm the atmosphere in this area of the developing storm. Because the clouds and water vapor distribution varies and the radiative heating rate depends on the cloud and water vapor, this drives spatial temporal variability in the radiative heating and cooling, which creates a potential for radiative feedback. Because now when you have variations in the amounts of these radiative heating and cooling, that warming can be localized, causing rising motion and an overturning circulation that can help the TC form, and I'm going to talk much more about in our talk today. And the reason that we want to study these processes is that there's really been sort of two lines of evidence on kind of giving more weight to the idea that radiative processes are important for tropical cyclones. The first sort of body of work has been mostly observationally focused, looking at the idea that tropical cyclones have a diurnal cycle. So as the sun rises and sets over the course of the day, we have variations in the structure of tropical cyclones associated with that. So this is an image showing the sort of so-called Dunyan diurnal clock, where basically at different times of day, you have this sort of ring of cold cloud tops associated with convection that then propagates outward with time. And based on the time of day, you can kind of predict what radius it will be at. And so this really kind of emphasized that, hey, the tropical cyclone cares about what's happening with radiation. And then the other really entirely separate body of work is the idea that these cloud-radiative feedbacks can help clouds or convection cluster or self-aggregate in idealized simulations, like this one shown on the bottom right with a SAM Marat's model, the global cloud resolving model version of it in our RCE intercomparison, where you have the separation of these convection into these moist regions with all the clouds and precipitation, and then these surrounding dry areas. And this occurs with totally homogeneous boundary conditions driven by these radiative feedbacks. So the idea then is to say, okay, seems like radiation might matter for convective organization and for TCs. How can we investigate that in the context of TC development? So our approach that we're taking is twofold. One, to do idealized cloud resolving model simulations with SAM, and the other to look at satellite observations of clouds and radiative transfer calculations. So I'm going to talk about the idealized simulations for really most of the talk, and at the end, I'll share some results from the satellite data. So the simulations that we're going to do use version 6.11.2 of SAM, in which we initialize the simulations from a mesoscale warm saturated bubble on an F-plane, but in an otherwise quiescent and moist neutral environment. And so the idea here is just to give it a kind of idealized initial disturbance from which a tropical cyclone could form. Our domain is about 2,000 by 2,000 kilometers with 2-kilometer resolution, doubly periodic boundary conditions. And the thing that's great about model simulations is you can go in and change things and, play God a little bit and turn different processes on and off and see what happens. And so we do that here, where we are going to compare the control simulation on the left, which has, full physics, interactive radiation, interactive surface fluxes, all of that sort of stuff. No convection schemes in these simulations. It's explicit convector representation. And we'll compare that to the one on the right, in which we horizontally homogenize the radiative heating rate at every level, at every time step. And so this removes the spatial variability in the radiative heating and thus removes any feedbacks resulting from that spatial variability. And so what's plotted here is just the hourly average near surface wind speed after an initial sort of spin up in which the model reacts to that bubble perturbation to create a weak vortex. We can see that in the simulation on the left with the radiative feedbacks, we've rapidly formed a strong circulation with a tropical cyclone, whereas the one on the right, we still have this weak broad circulation, but it's taking much, much longer for the wind speed to increase and that actually to contract into a tropical cyclone. It does get there eventually. And so radiative feedbacks are not strictly necessary for the tropical cyclone to form in these simulations, but they sure help a lot. It took about twice as long for the tropical cyclone to form in the simulation on the right as it did on the one with the left. And we can see this more explicitly by looking at the actual time evolution of the maximum wind speed at the surface. And we do a small sort of ensemble here by just adding in some small amplitude white noise on top of our bubble perturbation. And again, see that in our simulations in which the gray lines here, radiation has been homogenized and radiative feedbacks removed, it takes, maybe 6 days or so for the storm to reach tropical storm strength, which is 18 meters per second, whereas the one with the radiative feedbacks, it happens in about half the time. And we can see that again here by looking at the evolution of the convection and moisture. So on the left panel here, we show OLR, which is really an indicator, outgoing long radiation, an indicator of where our deep convection is. On the right, again, I'm showing it as an indicator, but the model doesn't actually feel these variations in the radiation. And then the other panels show the precipitable water. So again, with radiative feedbacks, convection rapidly organizes, deepens, and in association with that, we see moistening in the area of the developing cyclone and drying out in the domain surrounding that. Without radiative feedbacks, however, convection remains disorganized, shallow, and weaker, and moistening is slow to occur without that varying radiative heating to amplify things. Now, this, I think, is pretty clearly shows these radiative feedbacks have an effect on the TC development in these simulations. But as I mentioned before, radiative heating rates depend on a lot of different things. They depend on, both considering shortwave and longwave processes, as well as the dependence on water vapor, ice clouds, and liquid clouds. And so which part of that is actually driving this acceleration of TC development by the radiative feedback? So in order to address that,
we've got a quick question real quick.
Yeah.
So this, then the one with the radiative feedbacks, it seems to reach this maximum intensity or whatever, and then slowly linearly decay over time intensity.
Mm-hmm.
Have you run any of these simulations a little bit longer to see if the case without the radiative feedbacks does the same thing, or is it interesting in any way of why it seems to?
Yeah, that's a good question. I haven't run these particular simulations longer. I don't completely trust what's happening at the end of the simulations after the TC has formed, because it's the domain, the 2,000 kilometer domain is probably a slightly too small of a box to really fit this TC in. And in simulations of this type, basically the whole domain warms up after you form the TC, and that kind of reduces, the available energy for it. And you can actually then get into these long time period oscillations where the TC kind of decays and then reforms and decays and reforms. And so I think that's probably what's happening here. It's interesting about how the lack of radiative feedbacks might modulate that behavior, but here we're really focused in kind of the initial development, and these simulations are certainly not in equilibrium. Okay, so in order to figure out what is actually contributing to this, we remove the radiative feedback a slightly different way here. Instead of homogenizing it, I just specify a fixed profile derived from the simulation that had the radiative feedbacks, but the advantage there is we can do it separately for shortwave and longwave. And so if we can prescribe, say, the shortwave profile and allow the longwave to vary, so that removes the shortwave feedback but retains the longwave feedback, and vice versa. And so if we remove the shortwave feedback, we get this set of simulations, which doesn't look really any different than the control. On the other hand, when we remove the longwave feedback but retain the shortwave feedback, we get the set of blue lines here. And so, which is pretty similar or even more delayed when we were removing both long wave and short wave together. So this suggests that it's really the long wave interactions that are driving this feedback that helps accelerate TC development. And then we can say, okay, what is it about the long wave? Is it its interaction with the spatially varying water vapor or the spatially varying cloud distribution? And so to address that, we perform a set of simulations in which we specify the water vapor profile that enters the radiation calculation. And regardless of whether we do that for just long wave, just short wave, or both together, we get more or less the same result. Again, everything is kind of within the cloud of uncertainty of the control ensemble, suggesting it's not, at least not to first order the water vapor sort of radiation interactions. And I'll note here that here again, I was only specifying the water vapor in the radiation calculation. The rest of the simulation still is fully moist with dynamically varying water vapor. So that leaves us with clouds. But in these simulations, we have both ice clouds and liquid clouds. And so is one of them more or less important than the other? So we do another set of simulations where we go in and zero out the liquid cloud condensate in, again, just in the radiation calculation. This is equivalent to making the liquid clouds transparent or invisible to radiation. That gives us this set of green lines, which again is pretty much on top of the control ensemble. If we do the same thing where we zero out just the ice clouds, we have this set of cyan curves, which has a bit of a spread to it. There's on average a slight delay compared to the control ensemble. And then once the tropical cyclone forms, it seems to intensify at a little bit of a slower rate. And then if we zero out all the clouds together, we have this substantial delay that's sort of similar to if we removed all the radiative feedbacks together. So this is suggesting that it's really the cloud long wave feedback that is helping the tropical cyclone develop here, with the ice clouds having a bigger contribution than liquid clouds. And we can see that even more clearly by looking at the radial anomalies in the long wave radiative heating rate. And so this shows height radius plots where the center of the TC is at the bottom left of the plots. As we go through time, these are just daily averages over each day in the first 5 days of the simulation. So again, in the control simulation, we see cooling at the cloud tops, warming in the lower to mid troposphere below. The cyan contours here show a couple of contours of ice cloud condensate, the green, a couple of contours of liquid cloud condensate. The black solid line shows the radius of maximum wind. And so we have the situation where those radiative anomalies intensify as the tropical cyclone starts to form. However, if we've made all of the clouds invisible, there's not a whole lot to see. It looks very washed out on the projector screen, but it's washed out here too because there basically are no radiative heating anomalies anymore when the clouds are transparent to radiation. This spatial variability in the radiative heating rates has important implications for the resulting circulation. In the control simulation, this local low to mid tropospheric warming strengthens the tropical cyclone's overturning circulation, which is shown here, in which the blue shading represents air flowing inwards towards the center of the storm, red is flowing outwards away, and then the black contours are contours of vertical motion. So the radiative heating variability strengthens its overturning circulation, driving inflow that converges angular momentum towards the center of the storm in the lowest levels, and ascent, which contributes to moistening as well in our developing TC core. On the other hand, in our simulation with zeroed clouds, it takes much, much longer for that overturning circulation to develop. And consequently, much longer for the inner core of the tropical cyclone to moisten. So the right panels here show the same thing for relative humidity. Again, in the control simulation, already by day 3, it's nearly saturated throughout a deep layer of the atmosphere, but that does not happen until much later in the simulation when we don't have the cloud radiative effects. So this is sort of this mechanism that we're seeing where, again, these local lower to mid-tropospheric warming from the spatially varying radiation strengthens the TC's overturning circulation and contributes to moistening in the inner core. If we again want to confirm that it's really the ice clouds that are contributing most to this, we can look at the radial anomalies of these long wave heating rates in our, there we go, in our simulations with zeroed ice or zeroed liquid clouds. So the two panels on the left are the same two that I just showed previously, and the ones on the right are zero just ice or remove just liquid. So you can see that if we remove only the ice clouds, it's pretty effective at getting rid of most of the spatial variability in the long wave heating rate. We still have a little bit of lower tropospheric warming near the TC inner core from the liquid clouds. If we just remove the liquid clouds and have only the ice cloud radiative effects, on the other hand, this right column looks pretty similar to the control, again, suggesting that it's really the ice clouds that are playing the dominant role in driving this spatial variability in the radiative cooling rates. Now, given that, however, if you recall from a few slides ago, I showed that when you removed both the ice and liquid clouds, that had a much bigger effect on the development of the TC than removing either ice or liquid independently. And that suggests that there might be a nonlinear interaction between the two. And so to address that, we use the factor separation method to diagnose that interaction, where basically we have our simulations with either effect removed individually, everything retained, and then everything removed, and we can kind of difference them all to get both our linear sum of the ice and cloud liquid effects and the nonlinear interaction term. And those are shown here on the right, again, for these radial anomalies in the long wave radiative heating rate. So basically, the main thing that we see is that the left and middle columns look pretty similar. So overall, the long wave heating anomalies are well captured by the linear sum, especially that lower to mid tropospheric warming. The nonlinear interaction term, on the other hand, doesn't really have as clear or coherent a structure to it, but we do see magnitudes that are large in some places, such as above the freezing level, where there are mixed phase clouds, as well as associated with the deep convective cloud tops. And so you get kind of a little bit extra push when you have both the ice clouds and liquid clouds interacting together. Okay. So now the last thing that we do in these simulations to try to, again, fully understand the way that these different radiative feedbacks are contributing to TC development is to quantify their magnitudes using a budget for the column integrated frozen moist static energy variance. And this budget was first developed for studying convective organization in idealized simulations, and then adapted to tropical cyclones, as well as being used in both cloud resolving models and GCMs. And it's got lots of different terms here, and each of the terms involves an anomaly in the column integrated frozen moist static energy and an anomaly in a source or sink of that. And here the anomalies are taken as anomalies from the domain mean. And our sources and sinks of the MSE include surface enthalpy fluxes, the column shortwave flux convergence, the column longwave flux convergence, as well as advection. And so basically, if we have a process that is acting to increase the moist static energy of an already moist region, that is contributing to amplifying those anomalies, contributing to convective and moisture aggregation and TC development, and a positive tendency in this variance. On the other hand, if a process is acting to damp those anomalies or decrease the moist static energy of a moist region, that would be a negative feedback. And we see that in these simulations, this spatial variance of the column MSE increases with TC intensity. And this is really reflecting the fact that it's an effective measure for the local warming and moistening that occurs associating with tropical cyclone development. So basically, as the TC forms and intensifies, the moist regions near the center of the TC get moister, and the dry areas on the periphery get drier, causing an increase in that spatial variance. And we see that across all of our simulations here. And so this means that, okay, since this is associated with TC intensification, understanding then the role of those different source terms for the MSE variance can help us answer how these processes are contributing to TC development. And so here are all the different terms in this moist static energy variance budget. Focus just on the solid lines. The green line shows the surface flux feedback. The blue is the long wave feedback. The red is the short wave feedback. The pink is the advective term. And the gray line is the residual of the budget. Here we calculate this budget online at every time step in the model as it's running. And so it does close pretty well. The black line is the actual variance tendency itself. So the variance tendency is positive, during this first part of the simulation when the TC is intensifying. Early on in the simulation, both the long wave and the surface flux feedback are contributing. Later on, once you have an actual tropical storm, which is around day 3 or so in this particular simulation, then the surface flux feedback, which is really reflecting the wishy feedback, wind enhancements of the surface fluxes, really takes off as the biggest feedback. And so the long wave feedback contributes most in a relative sense early on, but even in the mature phase, it's still maybe a third of the value of the surface flux feedback as the TC approaches max intensity. So again, not saying it's like the most important factor, just an additional contributing factor. The dashed line is the simulation in which we've removed the removed the radiative feedbacks, and you can't see the blue dashed line because it's 0 in that simulation. But to understand that more explicitly, we can focus now just on the long wave feedback term here, and kind of look at that across all of our different simulations. Okay, so that's what's shown here, where now the colors indicate which simulation that we're considering, and I'm looking only at this long wave feedback. So this is, again, the contribution of spatial variations in long wave heating to enhancing moist static energy anomalies and thus aiding the TC formation and intensification. This is positive in all of the simulations that have a long wave feedback, suggesting it contributes to the TC development. And it's by definition 0 in the set of simulations in which the radiation is completely prescribed or completely spatially homogenized. In the set here where it's very, very close to 0, these are the ones where the ice clouds are removed in one way or another. For example, we can see here the green simulation, that's where only the liquid clouds are removed. That still has a long wave feedback. I'd also like to point out that if you compare the black line and the blue dashed line is the one in which we removed the long wave water vapor feedback, which before didn't really seem to have that big of an effect on the TC development, but it's not a 0 influence because, as you can see, that long wave feedback is reduced a little bit when the water vapor is held fixed. Now, one challenge here with comparing these different feedbacks with time in these simulations is, as I showed you, the tropical cyclone takes differing amounts of time to form, okay? So in order to kind of try to compare the different simulations on a little bit more equal footing, we can instead composite the value of this as well as other feedbacks over the snapshots in which the storm had a particular intensity. And that would remove any sort of intrinsic intensity dependence on these feedbacks. So that's what's done here. Here I'm showing just the results for when we've averaged the long wave feedback over the times that the tropical cyclone has an intensity of between 12 to 15 meters per second. So this is just before it's reached tropical storm strength. And then what's plotted on the x-axis, if we focus first on the figure on the left, the x-axis shows how long the simulation takes to reach tropical storm force. So how long does it take for it to form a TC? And the big difference you see here is the gap between this cluster of simulations and this cluster of simulations. And so the blue, gray, the bright blue and gray points down here, these are all simulations in which the cloud radiative feedback has been completely removed. And those take much, much longer to take tropical storm strength, to reach tropical storm strength than the ones that still have a cloud radiative feedback and thus have stronger long wave feedback. So this really says that sort of the existence of the long wave feedback helps the tropical cyclone form more quickly. But what about after the tropical cyclone has formed? Does it still matter then? So the plot on the right is showing now the same thing, the feedback at these early stages, but now it's plotted against the average intensification rate in the time after the tropical cyclone has formed. So once the TC has formed, how quickly does it subsequently intensify? And here we have a strong positive correlation between the strength of that feedback and the intensification rates, i.e. simulations that at a given TC intensity have a stronger long wave feedback have faster subsequent intensification rates, suggesting that having a stronger long wave feedback because of the differences in the representation of the radiative processes at one time makes it more likely the tropical cyclone will continue to intensify further and do so at a more rapid rate. Now, you might be wondering, is this correlation driven by just, again, these two different clusters of models, all these ones that basically have zero feedback? And the answer is no. If you actually remove all of these simulations and look just within the collection that do have a meaningful long wave feedback, we still have a significant correlation within these simulations. So again, even if the long wave feedback is existing, variations in its strength are correlated to the intensification rate. So to summarize the results from these idealized cloud-resolving model simulations, we have found that in these simulations, the radiative feedback significantly accelerate TC genesis and intensification. It's also true in realistic simulations of case studies of tropical cyclones, which I didn't include here for the sake of time. This is really contributed most strongly by interactions between ice clouds and long wave radiation, and it's supported both by these mechanism denial experiments we did, as well as the quantification by the moist static energy variance budget. And the mechanism is that the radiative effect of these deep convective clouds provides anomalous warming of the lower to mid troposphere that enhances the TC's overturning circulation and moistens the troposphere, contributing to TC development and intensification. So that's idealized model world. How about in the real world? Can we find evidence for these cloud radiative feedbacks in the context of tropical cyclones from observations? And so there has been some prior work done on this. For example, Wu et al. Used series measurements of radiative fluxes and found that intensifying tropical cyclones, these ones in this panel here, have greater radiative heating from clouds within the area of the tropical cyclones, and thus stronger cloud radiative feedbacks than the weakening TCs, which are the ones here. And so our goal is really to kind of extend this work to investigate the vertical and radial structure of radiative heating in tropical cyclones, decompose that into contributions from ice, liquid, clouds, and water vapor, and then evaluate the effect of the feedbacks from all those different components on the TC's intensification rate. And this is work being led by one of my graduate students, Sung-Young Lee. And so I thank him for sharing these slides. To do so, we use the CloudSat tropical cyclone dataset, which collects CloudSat overpasses that are within 1,000 kilometers of the TC center from 2006 to 2019. CloudSat is a W-band or 94 gigahertz cloud profiling radar. So it is basically just one single line that is scanning vertically in the atmosphere. And so this is an example of one, fortuitous overpass. So this is over tropical cyclone Finapi, I think, in the Pacific in 2010. And so basically along this path here, this is what the vertical structure of the clouds looks like. But since any individual TC is really poorly sampled, right? You might have just one overpass that looks like this. You don't have a full 3D structure at all. In order to achieve our goals, we need to composite over many, many overpasses, over many, many tropical cyclones. And to do that, we composite based on the intensification rate of the TCs. And so first we consider basically just tropical storms and category 1 hurricane storms that have maximum wind speeds of less than 42 meters per second, to focus on the weaker storms, because that was sort of where the modeling results suggested that these radiative feedbacks had a bigger impact. And we look just at overpasses that are prior to the time of lifetime maximum intensity. We then kind of take the time of the satellite overpass and calculate the intensification rate of the storm in the 24 hours centered on that overpass. And then we composite all those overpasses based on the intensification rate bins, everywhere from sort of storms that are sort of neutral, so not really strengthening or weakening, slow intensifying, fast intensifying, and then rapid intensifying. And these are following the bins used from prior work. So once we have things composited in that way, we can look at how all the different things vary. And so the first thing to look at is just how the ice water content itself varies through the different sort of intensification rate bins, as well as the water vapor. So here the water vapor is from the model product, but the contours, and shown in the colored shading, but the contours here show the ice content. So again, in the rapid intensifying cases, moist lower troposphere, lots of ice in the upper troposphere. If we look at anomalies then from our more slowly intensifying storms, we find that the greater intensification rates have greater water vapor and greater ice water content within 200 kilometers of the TC center. Okay, what are the implications of that for the radiative heating? We take the CloudStat retrievals and run them through the RTMG radiative transfer code to calculate radiative heating rates for our different composites. And so this is what that resulting calculation looks like for the long wave on the left and the short wave on the right. And here again, these radiative heating rates are plotted as an anomaly from the mean across the 0 to 1,000 kilometer radius. And so what we see here is similar to the model simulations. We see long wave heating in the lower troposphere and mid to upper troposphere close to the TC center, and long wave cooling at our convective cloud tops. We see short wave heating at the cloud tops and cooling below. Then if we compare how the more slowly intensifying storms compared to here, these are the rapidly intensifying cases, we have these panels here. And so basically, for the long wave where you see browns, that means that it's a negative anomaly compared to the rapid intensifying. So where it's brown, that composite then has less warming than the rapidly intensifying one does. For the short wave heating where there is purple, that means that there is less cooling where than the rapidly intensifying bin. So basically what we find is that for the rapid intensifying cases, they have greater long wave warming in their inner core than the more weakly intensifying storm winds. And so that's basically this brown patch here, which is sort of intensified in the upper troposphere. And when we compare it to the neutral cases, we also see a signal kind of in the boundary layer and lower troposphere. Similarly, for the shortwave heating, the rapidly intensifying cases have greater shortwave warming in the inner core. So these purples here in the inner core means less cooling in the other cases. And then they have greater shortwave heating at the cloud top. So essentially, the pattern of the radiative heating variations is just kind of stronger the more rapidly intensifying that it is. What's really interesting then is then comparing that across the different things that contribute to this variation. So we can run our radiative transfer calculations, allowing only the water vapor to vary across our different, or to have only the water vapor effect, or have only the ice clouds, or only the liquid clouds, or all of the different combinations. And so if we do that, that is what we see here. And so this is only for the rapid intensifying cases, just to limit the number of panels that I show you. And so the shading is, again, the anomalies in long wave radiative heating rate. The left panel is the same thing that I showed previously. The bottom one is showing the result from using only the presence of the hydrometeor. So this is sort of only the effect of the clouds. We've removed the water vapor influence here. And then the top right one is showing only the effect of the ice clouds. And the bottom is showing the effect of only the liquid clouds. And so if we compare sort of the top left and bottom left panels, we can see that they look pretty similar, again, suggesting that it's really the clouds that are contributing most to the spatial variability of the radiative heating. And it's particularly the ice clouds, because again, this top panel looks, broadly similar to the left two, whereas if we have only the liquid clouds, there's not really much variation in the radiative heating either. If you compare a little bit more closely, you can see that this sort of boundary layer sort of long wave heating in the top left panel, that's missing in the other ones. And so that's sort of contributed by water vapor. So the water vapor effect does contribute a bit to the lower tropospheric long wave heating variability. And again, we have some sort of interactions between the liquid and ice clouds, near the freezing level where both are present at once. Now, there's a bunch of other lines of these plots. The contours are stream function that is calculated using the Sawyer-Eliason equation. Basically, it's saying, what is the circulation that would result in a balanced vortex from this spatial variations in the long wave radiative heating rate? And then the little vectors show the actual circulation vectors. So again, these radiative heating variations drive an overturning circulation through the depth of the troposphere. If we only have the ice, we get most of that response, though the liquid contributes a little bit to enhancing the lowermost portion of that. Okay, and so this again is so far very consistent with what we're seeing in the model simulations. The last thing that we can do is then actually calculate the feedback term in the moist static energy variance budget. And so we do that here, where the MSE part of it, the temperature and water vapor, comes from ECMWF analyses co-located to the same overpasses, but the radiative fluxes come from our RTMG calculations. And we show this first here as a function of radius. And here, these are zoomed in just on the innermost 300 kilometers of the storm. The red shading is the composites over the rapidly intensifying cases. The orange is over the fast intensifying cases, green, slow intensifying, blue, neutral. And then we have that separately for the shortwave feedback on the top, long wave feedback on the top, shortwave feedback in the middle, and then the net at the bottom. And then the other panels show the radius weighted average of these different feedbacks over different radius areas. And so average over 0 to 200 kilometers, or average over the full size of the area we consider 0 to 1,000 kilometers. And so if you take a look at the bottom panel, what you notice is that this is the total radiative feedback. All of these lines are positive, basically. It's saying that we do, in the net, have a positive radiative feedback on tropical cyclones. And so these radiative variability is contributing to moistening the TC core and enhancing TC development. If we look at the long wave feedback, we see that the red line is the biggest, okay? So the rapidly intensifying cases have the greatest long wave feedback. And if you then separate this out again into the feedback resulting from all the different components, cloud, not cloud, ice, liquid, etc., this again is resulting mostly from the ice clouds. If we are averaging over the innermost 200 kilometers, as we see here, again, these rapidly intensifying cases have stronger feedbacks than all of the more slowly intensifying ones. The error bars are the 5 to 95% confidence intervals on all of this. On the other hand, if we're averaging over the whole 0 to 1,000 kilometer radius, we don't really see, certainly not any statistically significant difference between our different intensification rate bands. And so the storms that are intensifying at different rates, the differences between them are really prominent only kind of in the inner core of the TCs. Certainly within the innermost 200 kilometers, and really most prominent within, say, the innermost 150 kilometers. If we look at the shortwave feedback, it's small, it's much smaller than the long wave feedback, and it's kind of close to 0 for most of the simulations. For the rapidly intensifying cases in red, it's actually a negative feedback. And that's due to the effect of clouds. Basically, these rapidly intensifying storms have so much ice water content and thick cloud cover that it actually reflects a lot of the shortwave or solar radiation before it can penetrate the atmosphere and be absorbed. And so if you calculate the clear sky version of the feedback, that is positive for the rapidly intensifying cases, though it still is a bit weaker than the more slowly intensifying ones, because again, the clouds are just blocking a lot of stuff from getting in there in the first place. And so there's some sort of competing factors going on there in the shortwave. But since it's so weak, when we add them together, it's really the long wave that's dominating the net. And I would say that all of this is consistent both with the prior observational work that has been done, as well as the model simulations, both that I just showed you as seen by, and as well as seen by others as well. So to conclude, we've discussed both idealized cloud-resolving model simulations and satellite observations that seem to agree that radiative feedbacks contribute to TC development. And it's really the effect of ice clouds on long wave radiation that's the most important. We found that the long wave cloud feedback is stronger in TCs that are intensifying more rapidly. This is true both in the observations and in the models. And we found in the models that the existence of these long wave cloud feedbacks can accelerate the initial formation of the TC development. That is harder to evaluate in observations, at least with the current data set where we are only looking at these overpasses, basically based on times that the tropical cyclones are in the best tracked data set, which means they've already formed. But it would be really interesting in future work to try to track back earlier in their life cycle to the sort of pre-genesis stage and see what the sort of structure of the radiated feedbacks would look like then. But all of these results suggest that improving the representation of these cloud-radiated feedbacks in forecast models has the potential to yield advancements in TC prediction, especially with regards to this rapid intensification process, which is where we're seeing the biggest differences. And that's the thing that we struggle the most with in a forecasting standpoint. So again, the observational piece of this is ongoing. We hope to submit. Sung-Young is working on writing the paper on that should be submitted later this summer. The modeling stuff was published last year. And so with that, I thank you guys so much for your attention. Also note that the realistic simulations I didn't have time to talk about are in this bottom paper if you're interested. So thanks so much, and I'd be happy to take any questions. Let me see if I can recover my Zoom control panels so I can see if there's anything online.
I have it open, so I can tell you there's no
Okay.
questions right now.
Okay. Yeah,
I'll start with a question, which is, so you ended with the motivation of, right, if we better understood these and had them included in models that maybe we could better forecast.
Mhm.
But I guess maybe I have even a more first order question, which is, why is it, why do certain conditions have the conditions that are right for the feedback and others don't? So is it aerosols? Is it the environment? Like what? I mean, I guess the work that you were talking about towards the end there, maybe you could start to look at some of those other fields and see, but I'm curious.
Yeah.
If you have thoughts on it or if you've looked at that.
So we have not considered the effect of aerosols in our radiation calculations from the satellite observations. Of course, the aerosols that are present may influence the cloud distribution. And so the indirect effect is there. It's something that could be done, but would require different satellite observations than what is in this particular data set. The one thing that Sung-Young has done is, he has looked at the relative contributions of the ice or liquid water concentration compared to effective radius and how those populations are varying across the different composites, basically. So, because especially for long wave versus short wave, at least my understanding of it, and I'm not a microphysics and radiation expert, but my understanding is that for the long wave effect of hydrometeors, it's the actual amount of water that is more important. But for the short wave effect, the size can be really important as well. And so he basically redid the radiation calculations by holding, say, the ice water concentration constant across all the different cases, but allowing the effective radius to vary, and then vice versa, and found that it's really just the amount of ice that matters. And so the reason that the rapidly intensifying cases have a stronger radiative feedback is because they have way more ice in the inner core, basically. So then the question becomes, why is that the case? And then that is maybe where you get into more of these questions about aerosol properties, environmental properties, microphysics, etc.
Yeah, okay. So if I could follow on real quick, which is, so our first seminar speaker this semester was Kieran, who had talked about rapid intensification and observations, and that it might be changing, right, in a warming world. And there's been some suggestion that there's a trend. So that kind of so have you done any of the idealized simulations with different SSTs and see if the role of the feedback becomes larger or in warmer?
Yeah.
To like link to this potential fact that there's maybe been a trend, but
An
also in the
increase in
North Atlantic, the trend could be because there's aerosol changes as well. So
Right.
It's hard to.
Yeah. So I haven't done these particular simulations at different SSTs. I've done simulations of spontaneous TC genesis at different SSTs, and there were some variations in the strength of the feedback with SSTs, but they were not very intuitive, and I don't understand them yet, and we haven't followed up on that. I will say, though, that there's been some other work done by Bosang Zhang and people at GFDL that have looked at these processes in climate model simulations and have done simulations sort of with and without the cloud radiated feedbacks using cloud blocking experiments. or really not cloud blocking, I guess, cloud radiation blocking. They like use the climatological radiation instead. And then done that at different, CO2 concentrations and so on and so forth. And I think, if I recall, they found that the effect of the radiative feedback in enhancing TC development was weaker at warmer SSTs, but I at least don't have an explanation for why that is. Just thinking about kind of like where it's coming from here, I guess, what would change the magnitude of it? The amount of ice. So we think in a warmer world, there'll be just greater amounts of, ice water, because more water concentration. But, and it might also be higher in the atmosphere, which would also probably enhance the feedback. But then what also really depends a lot is how sort of spatially concentrated it is. And so if the scale of the TC increases, that might reduce the feedback, right? If the ice is sort of more spread out rather than concentrated, because this is all dependent on spatial variability, not just absolute magnitude of the radiative effect. So yeah, it's a really interesting thing to think about, and yeah, try to see how this would change in a warming climate. And because I think it does have that potential. And I would say the other thing about, I'm saying improving the representation of this in forecast models. I'm not saying that forecast models don't have this feedback in it. They do, but we already know that forecasts are sensitive to say how microphysics is represented. And I'm just more suggesting that, thinking about some of that sensitivity from the lens of the radiative effect, not just the sort of microphysical heating, is, it might be even more important, I guess, than we even think. And so, yeah.
Especially in the data assimilation part, right? So,
Right.
I think Edmund raised his hand online.
Yeah, I think you can ask and we'll hopefully hear you.
Yeah,
Online.
great talk. Yeah, yeah, actually, you just answered my question, or you because that's basically what I was trying to ask. Is basically, yeah, you got this feedback from SAM model, but I would imagine that this something like that would be present also in models like HWRF, which they are using although the microphysics may be different, the radiation may be different, but yeah. How do you assess which is better than? So
yeah. So I mean, just to repeat it to make sure everyone in the room heard, the question was about, we looked at this feedback in one model, but it's also present in other models. How do we assess, which is better? I think that's where these comparisons to observations come in. Like, there's all sorts of different methods that are used to validate hurricane forecast models. And I might be wrong, but I don't think people have typically before looked at the cloud radiative feedback as one of the things they're evaluating in it. And so in terms of, again, choosing how you're sort of setting up all the different parameterizations in the model, thinking about this particular mechanism and feedback is maybe one of the things that should be looked at. And so in order to do that, that's why we need these sort of observational analyses, because that is the truth, I guess, that then the models can be compared with. And so, yeah, these processes are in the models, as I said, but they certainly are different across them, both through differences in the microphysics representation, and then from that, the optical properties and radiative properties of the different clouds. And so, yeah, it's something that I think has not been, it hasn't like this, we haven't taken advantage, I guess, of this particular mechanism as something that could help us improve our forecasts yet. And I think the evidence here suggests that I think it's worth looking into more and doing more of these sort of model observational comparisons. I have another student in my group who's also looking at some of these processes using dropsonde data from Hurricane Hunter aircraft. I know also some work in Brian Tang's group at Albany. They're looking at some similar things, including how the radiation scheme that you use affects these processes and things like that. So yeah, I think it's definitely a challenging thing, but I think it has potential.
yeah, thank you.
Yeah, thank you for that fascinating talk. I'm so happy to see ice clouds and ice cloud microphysics as well. Just to I have millions of clouds. Just to understand some things. I mean, could you elaborate on the correlation you saw between liquid clouds and the ice clouds? You mentioned the linear term, non-linear. If I'm naive, so you mean you need liquid and ice? Does it mean for immersion freezing that if that is happening, you need a liquid cloud? So you cannot make an ice cloud without the liquid cloud.
Mhm.
And could you deconvolute it in such a way for an interpretation of the ice formation path? Could you use that kind of correlation? So that was one maybe naive question,
Mhm.
because if there's a correlation, there are different ice formation modes. You have this huge extent, but you have so much moisture, and it will be all sea spray aerosol mostly. That's an accurate solution. So it will be liquid likely, 99%. So that could be a really cool indication that they first have to take out water, then they freeze heterogeneous.
Yeah.
So that would be one naive comment.
I think, yeah, that's a really interesting comment. I mean, I don't even think I know enough about microphysics to answer, but something, I guess, even simpler maybe than what you're thinking of is just the fact that when you're looking at, okay, the radiative effects of ice clouds with nothing underneath them is different than the radiative effects of ice clouds with liquid clouds underneath them.
I'm not surprised.
And I think that more is the difference that's coming up in these sorts of things.
Yeah,
And-
that leads a little bit to my another comment or question.
Okay.
I thought, and you answered that in part to Kevin, in a way, if you could back up the number of ice crystals or sizes from your radiative transfer model.
Mhm.
Now, you said it's all about the ice water content. In a way, I agree, but Vendish and others have early shown just changing the ice crystal shape,
Mhm.
same ice water content. You get changes in the radiative flux of hundreds of watts per
Yeah.
square meter. Okay, so even if you do the sensitivity analysis, you keep the number, the total content the same, you change the number, but you don't change the ice crystal shapes. And that answers your second one. If you have no liquid clouds below it, you likely have a different formation mechanism of the ice, different conditions to get different ice crystal shapes.
Yeah.
So you can have completely different radiative fluxes.
Radiative fluxes, yeah.
So that all is connected, and therefore, I mean, it's really fascinating. I have not seen that kind of interpretation. So
Yeah. I think, yeah, that's another, I think, motivation for, yeah, taking a closer look at some of this and observations, because I am confident that all of these models are representing all of that completely wrong. So, the other thing, though, I would say in response to that is, yeah, just to clarify here, when we remove the ice clouds or remove the liquid clouds, we're only removing their radiative effects. Yeah, so like they're still there.
That's the beauty of models.
Yeah,
Therefore,
yeah.
I'm thinking you could do a sensitivity and see how it fits the
Yeah.
microphysical interpretation. Anyway.
The other thing in kind of, yeah, relation to your comment about this, yeah, interaction between the ice and liquid, I just want to show this because one of the things, right, we had these simulations with zeroed ice, zeroed liquid. They both kind of slow things down a little bit, but then adding them together is a much bigger effect. Part of that is, I think, actually through compensating influences. So if you look at this bottom lower plot, for example, this is the shortwave heating in the simulations. And so in, say, the black line, for example, that's the control. The shortwave heating is lower near the inner core because all these clouds are reflecting the radiation, right? When we remove the ice clouds, that's the blue line. So when we don't have the ice clouds, now the shortwave heating is stronger in the inner core because it can actually penetrate down and be absorbed and interact with liquid clouds. And so,
because it's a thick ice cloud.
right, exactly. And so they definitely don't add up completely linearly. And this is just one of those things. And I think all of the different actual cloud formation mechanisms that you're suggesting are an even bigger add-on effect after this. And yeah, it's complicated and fascinating. Thank you for your comments.
I know it's running late, but a quick question. Is it because of the phase of the cloud particles, ice versus liquid,
Yeah.
or because of the position of the hydromedia?
That's a great question. And I really need to just do this simulation and like swap like which variables I send in for ice and liquid. I think it's probably just the height. I think that's maybe the most important factor. The phase does matter for the radiative effects, but I think the fact that the ice clouds are high is probably the bigger factor. But yeah, I think someone asked that question, and every time I give that talk, and I need to just do the simulations so that I can answer it.
Yeah, from the long wave perspective, it seems to me like the position.
Yeah, I agree.
matters more than the phase.
I would agree.
Sorry to dampen your.
No, it's really important why it forms up there.
In the first place, yeah.
It's much bigger than a cirrus cloud.
Yeah,
So the
definitely.
budget is, and that comes to aerosol. In principle, if you can deconvolute your radiative transfer model, tell how much ice crystal there is, then you can make a back of the envelope calculation if there's enough aerosol, which can make all of it. Or
Okay,
you don't even need to run a complicated model, just with the known parameterization
Yeah.
they have. So in a way, you're not, no height is important, of course. The amount is a question.
Yeah.
I mean, it has to nucleate.
Right.
To nucleate of the aerosol.
yeah, so both the amount and where it is in the atmosphere.
That's complicated.
So-
Thank you.
So maybe we can continue at lunch, discussing it. I think it's great. Should have pizza next door in the Swanson room by the library. Graduate students, meet with Allison at 2, for a conversation with her. And yeah, please, let's thank Allison.